All right, this is an experiment that I'm going to end up videotaping here. Obviously, not really experiment, just a demonstration to help you guys a little bit more with a graphing activity. And what you can obviously tell is this is a hot plate that I swiped from the chemistry department. Brought it home here for several different videos that all kinds of teachers are making from home now. But that's just a regular old chemistry class hot plate. These are two separate temperature probes, they call them, for vernier or Lager Pro, that hopefully you guys are somewhat familiar with by now. But those then temperature probes are both monitoring, obviously, the temperature of the water. The hot plate's heating the water, obviously, and on the computer screen, what you see are the two different temperature scales that I'm measuring that temperature in. All right, and what you guys are gonna do is every so often throughout this video, write down corresponding Celsius and Fahrenheit temperatures, all right, at whatever time interval you care to. It really doesn't matter. Write down corresponding Celsius and Fahrenheit temperatures, okay? So right now would be a great time to do it. I don't know, right now I'd say 25.8 and 79.6. Write them both down. If they're not exactly the same, or if they change a bit between writing them down, that's fine. So wait, I don't know, a minute later, write them down again. So right now you got what, 26.3 and 80.1. So you're going to have corresponding data points of Fahrenheit and Celsius, or I should say Celsius and Fahrenheit, and you're going to make a graph. Okay, that graph is going to have Celsius. There's Celsius on the axis. All right, so your axis is going to be Celsius. Your y-sis is going to be Fahrenheit. All right, so you're going to have a bunch of dots there that make a line, obviously. Celsius on the X, Fahrenheit on the Y. Once you have all those dots plotted, and we'll wait till this goes up to a boiling point, obviously, which you hopefully already know what those two numbers are going to be. Once we get that to a boiling point is when we're done. So this will, be about as much fun as watching water boil. But every so often, write down corresponding numbers. So when you make the graph, you'll just do a scatter plot. It'll just be plotting X's and Y's. Get a line of best fit for those dots, all right? When you get the line of best fit for those dots, calculate the slope. The slope of that line, you should kind of see, that's the relationship between changes in Fahrenheit and changes in Celsius. And then the really kind of neat thing about this activity is what I want you to do is extrapolate, which just means take the line that you draw within the region of data that you know and extend it outward to regions of data that you don't know. Specifically, extend it towards the y-axis. And where does that line intersect the y-axis, what I call the y-sis? Where does that line hit the y-sis? At that location, I want you to really kind of emphasize what that number is and explain what the significance of that number is, the y-intercept. So what you're going to end up creating is a y equals mx plus b. M is obviously the slope of this line. Y is what I told you to make the y. Y is the Fahrenheit temperature. So you'll have the temperature in Fahrenheit equals M, which is the slope that you're going to end up calculating, times X, and X is going to be your temperature Celsius, plus B, and the B you will hopefully see a number that you recognize, and tell me what that plus B is. All right. And so hopefully, as I've been talking, you've also been writing a few more of those corresponding Celsius and Fahrenheit. So shoot, right now I'd write what, 36.5 and 98.5, whatever. I know they're climbing. That's good. We want them to, as they keep going, again, just make a data table as best you can. And you're going to end up we're going to get graphic. We'll be getting graphic, but it's all right. We'll just see the relationship between Celsius's and Fahrenheit's is. It'll help you generate the equation that is how you convert between the two. Um, but it's just an activity that helps you see graphing, helps you see where conversions come from. It might also be interesting to kind of look up the differences, why there is a difference between a Celsius and Fahrenheit scale, who came up with the Fahrenheit scale, what was the reasoning behind using the scales that they did, who came up with the Celsius scale, what was the reasoning behind doing what they did. But yeah, boy, these numbers are climbing. But we got what 41.8-ish and 108.1-ish. So we're getting some decent data here. But again, it's a little slow. But hey, you can't rush physics now, can you? All right. In this particular graph, it goes along very nicely with the graph that you guys just made using centimeters and inches and getting the slope of that to tell you the conversion between the two. Because what's kind of hard for a lot of students to visualize is conversion factors. They are graphs, all right? They're numbers, but a lot of students or just people in general don't associate that particular number with it's an actual graph. I mean, that's how you come up with conversion factors. If this much equals that much, or this corresponds to that, then those changes are based on graphic simulations like this one. This isn't even a simulation, this is a real conversion here. But yeah, it's even though it's just one number, it's a y equals mx plus b. So if y equals mx, then y equals some constant times x. That's it. And if y is centimeters, it equals some constant times inches. That's mx. And then the plus b, in that case, the b would be 0, because if you have none inches, I'm pretty sure you're going to have none centimeters. So the ability to recognize that y equals mx plus b is showing up in this activity is a neat thing. It's a skill to have, to recognize that everything is just coming from the graph. So even if it doesn't look like y equals mx plus b, this sometimes equations look like y equals kx. Well, the k is just another way to say the letter m. That's all. And y is some constant times x. So on your inches to centimeters graph, the number of centimeters equaled some k constant, which hopefully you guys got 2.5-ish, times x, times the number of inches. That's it. And so you can, that's y equals mx plus b, y equals kx. The b is just 0. Well, in this particular x example, there will be a b, which is a y-intercept. So in other words, it's how much y do you have when x is 0. I mean, that's it. That's it. You guys know when you make graphs, there's really only two things you can do when you get graphic. And it's either calculate a slope or calculate an area. All right. And the way I help students kind of figure out which one of those two to use is just realize slope just means push the divide button. That's all. Slope means push the divide button. Area means push the times button. That's it. I mean, that's all you got to do. Am I dividing or am I timesing? That's the only decision you need to make. And what helps you make that decision are what are the units that the y and the x are communicated in. And if you want to say y is, in this case, degrees, what I say, Fahrenheit, and the x is degrees Celsius, then if you push the divide button, it's Fahrenheit per Celsius. That makes a little more sense than pushing the times button, calculating an area. It's a Fahrenheit times a Celsius. It's Fahrenheit Celsiuses. And that just doesn't really make much sense. But it would be Fahrenheit per Celsius degree. That kind of makes more sense. When you guys were doing your inches on the x-axis, centimeters on the y-axis, and you then would just say, hey, tell me the conversion factor, but I don't tell you to take the slope or take the area, then that's a decision you guys are going to have to logicate your way through. And again, the way you logicate your way through that decision is to say, okay, am I going to push the divide or am I going to push the times? The way, again, you make your decision is to say, all right, does it make sense to push the divide button? Do I want centimeters on the y-axis per inch on the x-axis? Centimeters divided by inches, cms per inch. Or do I want to multiply the two? There'll be centimeters times inches, cm inches. And when you multiply those two, again, it really doesn't make sense. It's just gibberish to say centimeter inches. But it does make sense to say centimeters per inch. And when you have centimeters per inch, you now have a conversion factor, which is dancing around 2.5. So another skill to develop is when you guys are making graphs, or as you have been for many years, realize there's only two things you can do: slope or area. Slope just means divide, area just means times, and what you're doing are the units that the y-axis and x-axis are communicated in. You're either dividing them or multiplying them. All right, that's a good one to have. But anyway, what are we eyeballing here? 70-ish degrees Celsius. Hopefully you've been writing some more of this data down. And we're at what, 160-ish Fahrenheit. Good. Hopefully we're getting there. You guys, I'm sure, know what the boiling point of this stuff is going to be in both temperature scales. But yeah, if you got those written down or those already known, that's good. Maybe you already know what the freezing point of those are. And that is then a number that will help you recognize if your y-intercept is, in the right neighborhood. But, like I said, this activity, it's about as much fun as watching water boil. The suspense is killing me. But anywho, I'm happy to be doing this sort of stuff. It's neat to have some interaction with students after we've been in a quarantine for 5-6-ish months now without ever really leaving the house. It's just something that I hope we get back to here before too long. And maybe this is bringing back some chemeries for you, huh? Happy chemeries. But yeah, some of our chemistry teachers I hung out with a bit this past week as we were in school getting ready for you. And it was neat to see those folks again, but it's funny, we're all wearing masks and we're afraid to get too close to each other. But hey, we'll see. Physics is hopefully stronger than biology, but I don't know if we get a little too much biology flying around the high school, if it won't mean we can't go to physics anymore. We're getting there. We're getting there. We're seeing bubbles, some tiny bubbles. Where are we at? 81 and 179. Well, we have an update on that. 180-ish. But yeah, hey, yay physics here, huh? What do you think of the kitchen? Yeah, works for me. All right. As we gather some more data here, You see the bubbles? Oh, that's my box. Oh, masks. Oh, fun stuff. We're getting there. We're getting there. Oh, yeah. All right. Move her over. Telling you, suspense is killing me. It's killing me. So, while we're waiting, can I get you a beverage? Oh, yeah. Good stuff. All right. Come on. Come on. Oh, yeah. Well, maybe we could listen to the radio. Huh? Yes, that we provide our clients. Don't move out of your house just because your wife tells you. Yay, commercials. Gotta love them. Perhaps a snack. Yeah. Writing a few more down. 92 and 199. Huh? I'm gonna get to see what 100-ish Fahrenheit is. Ooh, 200-ish Fahrenheit is a little less than 100 Celsius. Huh? Ooh, maybe you guys already know some numbers-ish on the Celsius scale. But that would be another neat thing to look up. I mean, you guys could get on the internet and just see, hey, what temperature scales are in different units. And maybe you guys have done that in physical science classes, but usually room temperature is a neat number to know, just what it is in Celsius. What your body temp is a neat number to know in Celsius. And then obviously boiling points and freezing points are neat numbers to know, but those are usually the markers in terms of where what numbers you'll see. But we're getting close here, obviously. Where are we at? 90, I can't see it, 95. So we're getting there in 205. So we'll see if these guys give us what we want here, but we'll let it go for another few minutes. Obviously, we've started boiling. I don't think it's quite what I would say is a nice, good, healthy boil here. But we're, it's almost there. It's good. We'll take data for a few more minutes here, see if we can get her up to the numbers that I'm sure you already know are the boiling points in Celsius and in Fahrenheit, right? Yeah, maybe you can hear it on the microphone. I don't know, but it's got a good noise, a good tone to her. Oh yeah, getting there. Getting there. I'm gonna give it what we've been taking data. We're not quite to 20 minutes now. Boy, I tell you, time flies when you're having physics. And we'll just kind of pay attention to see if these stop climbing. And if they just stop climbing, then that means, well, gosh, we've reached the boiling point, which means we're essentially done. Now, I know you guys are probably looking at these numbers and saying they're off a little, and I can't argue with you. These numbers are off a little. It could be a function of well, many things actually. Maybe that's something you guys should do is write down the reasons that are the potential explanations why that's not the exact number that you've always been taught your whole life is the boiling point of high quality H2O, and why that isn't the exact number that you've been taught your whole lives is the boiling point of high quality H2O. Okay, so I would include that. So go ahead and actually include that in your lab write-up. So remember what you're going to do. You're going to put this on the x-axis, these numbers. So however many of these numbers you've collected, hopefully at least like 10-ish. Good Lord. 10 of these numbers that correspond with 10 of those numbers. You'll have a scatter plot with dots in it. Calculate the slope of the line. Tell me where it intersects the y-axis, and then write the formula for the line. The temperature Fahrenheit equals M temperature Celsius plus B, whatever that B intercept could be, C, and then come up with some explanations as to why that isn't the exact number you've been taught your whole lives, the boiling point Celsius, why that isn't the number you've been taught your whole lives, boiling point Fahrenheit. But anyway, gosh, I don't know. Beyond that, it looks like we've done what we came here to do, and who knows, yay, physics.